All right, so welcome to this first lecture on the simplex method. This lecture will be a tutorial in 3 acts, and the first act is going to be on the standard form linear program. So we are going to take any LP and reduce it to the standard form. Okay, so that's the first act. Then we are going to talk about dictionaries, where we present a way of organizing the problem as a dictionary, and we are going to conclude this with a lecture on an act on pivoting, where we are going to talk about how to do pivoting, which is the key part of simplex. And finally, I'm going to put it all together and give you an example along with a geometric interpretation of simplex. It's never too early to start, and I'm going to do that. All right, so that's the agenda for today. So let's start with the first act. This is going to be a revision of material that's already been covered by the lecture on LP formulations that was delivered by my co-instructor Shalom. And what I'm going to do here is going to be a revision. It's going to be a recap of things that you should already know. Right, so why are we interested in converting the problem to a standard form? And the main reason to do that is it recalls some words of wisdom by this famous mathematician, George Polya, who wrote this fantastic book called How to Solve It. And in his book on how to solve it, what George Polya advises is simplify the problem. Try some related problem that's as simple as possible, and try to see if you can solve it first before taking on the whole weight of a complicated problem. And certainly linear programming is a complicated problem, and therefore we should start with a simple problem. And therefore, in the spirit of doing that, we are going to reduce the problem to a standard form. Okay, so let me recall. So this is your standard linear program. We'll do maximization of an objective subject to some linear inequality constraints. Okay, so far you should know all this. Okay. I like to write things in matrix form, so this is C transpose X, maximization of C transpose X, subject to AX less than equal to B. Okay. C is the column vector, C1 through Cn. X is the set of decision variables, which is the column vector X1 through Xn. A is a M times N matrix. And B is a column vector, B1 through Bm. M is the number of constraints. N is the number of decision variables. Okay, so far that's the problem setup. Now in the standard form, we have the same set of constraints along with these extra non-negativity constraints. Okay, so this is the standard form linear program. A standard form linear program is a linear program of the same form that we saw in the previous slide, except that we now have this extra constraint that all the variables, all the decision variables involved in the problem are non-negative. Okay, and this seems like a restricted form of a linear program, and we call this the standard form. Okay. So in matrix notation, the standard form is again maximize C transpose X subject to the constraint AX less than equal to B, and this extra constraint that we tack on, which is the non-negativity constraint. Okay, so that's the standard form. All right, as an example, here we go. So here is the objective function. Remember, we are maximizing the objective. Here is the B vector. The A matrix is encoded in here. Decision variables are x1, x2, and x3. And don't forget this constraint, x1 greater than equal to 0, x2 greater than equal to 0, and x3 greater than equal to 0, that we conveniently write in just one shot as x1, x2, x3 greater than equal to 0. All right, so what are we going to do with the standard form? So the first thing is to note that if you take any linear program in your favorite form, there is a conversion of the problem to a standard form problem. So you can put any linear program to a standard form linear program. And one of the things to note is that the standard form is going to have a different set of decision variables, maybe. It's going to have a different objective, maybe, different set of inequalities, and it's going to have this constraint z greater than equal to 0 that makes it a standard form problem. Now this conversion is not complete unless I also show you how any solution from here can be converted to a solution to here. Okay, and these two are easy conversions. So computationally, we would like these two to be very easy conversions. Okay, and this kind of a conversion in computer science is called a reduction. So we are reducing from solving any LP to solving a standard form LP. Okay, and how do we do this? So Shalom in his lecture has covered some of how we do it. I'm just going to give you a quick recap on how to convert any LP in your favorite form to a standard form LP. Okay, so let's look at what are the problems when converting to a standard form. So here is my favorite LP, and it's not in standard form. And there are 3 things that cause it not to be in the standard form, or maybe more than 3 things, 4 things. Number 1, in standard form, we like to maximize, and here I'm asking to minimize. Is that an issue? In standard form, I do not have equality constraints, and here I have a constraint that's actually an equality. Is that a problem? In standard form, all inequalities are less than or equal to, and here I have a greater than or equal to inequality. Is that a problem? And finally, what about x2 greater than equal to 0? And what about x3 greater than equal to 0? So these have gone missing. Is that a problem? So what we have to do is convert this problem to a standard form while trying to overcome all these difficulties: minimization versus maximization, equality constraints, greater than or equal to, and missing non-negativity constraints. So if we can tackle all of this, then we can take any problem and convert it to a standard form problem, as I said in the previous slide. Okay. Now this is not going to be rocket science. This is very simple, of course, but I'm just spelling out to you how we go and do this step by step. It's extremely simple. I'm not making it complicated. You should understand that. But we are just going to see how to do it algorithmically. All right. How about objective direction? So let's start with minimize, and how do we convert it to maximize? Very simple. You just change the sign of the objective. So if you want to minimize C transpose X, you maximize the negation of C transpose X. Okay. In other words, if you want to minimize this objective function, you maximize its negation. So you multiply it by -1 and you maximize its negation. Very simple, and that takes care of changing minima to maxima. And of course, when you change the solution back, you have to negate the solution. So if you get an objective value of -20 here, then you have to negate it and get an objective value of 20 here. That goes without saying, but to convert minima to maxima, you negate. Very simple, nothing great going on, hopefully. All right, how about equality constraints then? An equality constraint is just 2 inequality constraints. So if you want to say x equals y, alternatively you can say x greater than equal to y and x less than equal to y. So therefore, you can take any equality constraint here and you can get 2 inequality constraints. Therefore, equalities are not a problem, right? Okay, and what about constraints that have greater than or equal to? Well, that's really simple. If you have x greater than equal to y, you convert that to -x less than equal to -1. Okay, so everything can be changed into less than or equal to. And again, this is really elementary things that you should know from high school. I'm just making it more formal and spelling it out here because you may have to program this, and that's why I'm spelling this out. So for instance, when you have this, you convert this to this. So this is very elementary. So the last thing, which might be slightly more non-elementary, is how do you deal with a missing non-negativity constraint? So if you are missing a constraint that says a variable is non-negative, how do you deal with it? Okay, you can't just add this constraint. If you just add this constraint, you are completely changing the meaning of the problem. So it's not good to add this constraint. Okay, so the way we do it is a small trick, which we call doubling the variables trick. Okay, so this trick is very simple. Take any variable xi, and double it up to introduce two fresh variables, xi plus and xi minus. Okay, these plus and minuses are just subscripts that you add onto it, and you rewrite xi as the difference between xi plus and xi minus. Okay, and this is something that Shalom should have covered in his lecture, and the key idea is that any number, take a number 7, can be written as the difference between two non-negative numbers. So 7 can be written as 7 minus 0, and minus 7 can be written as 0 minus 7, or if you wish, it can be written as 2 minus 9. Any number can be written as the difference of two non-negative numbers, and therefore you can afford to say xi plus is greater than or equal to 0 and xi minus is greater than or equal to 0. So you replace, wherever xi occurs, you replace it with this expression, xi plus minus xi minus. In some sense, xi minus talks about the negative part of xi, and xi plus talks about the positive part of xi. And together, their difference covers the entire real line. Okay. As an example, here we have our favorite LP again, which has a minimize, an equality, a greater than equal to, and then missing x2, x3 here. Okay. So how do we convert this to a standard form? We go through the steps. Minimize becomes a maximize. Okay. Because x2 greater than or equal to 0 is missing, you say you add two new variables, x2 plus and x2 minus, and wherever x2 occurs in your problem, you replace that by x2 plus minus x2 minus. Likewise, wherever x3 appears in your problem, you replace that by x3 plus minus x3 minus. You perform the replacement, so this x3 here gets replaced here by an x3 plus plus x3 minus. Okay, and likewise equalities get replaced by two inequalities, and greater than equal to's get replaced by less than equal to by negating both sides. So after doing all this transformation, you get this linear program. I'm not going to take you step by step through this. It's not important that we do this, but if you get the idea of how this works, then we are good. All right, but do not forget that when you do this, you have to transform the solution back. What does it mean? So if you have a solution to this right-hand side problem, then you have to re-transform it back in terms of x1, x2, and x3. Okay, since x2 is just x2 plus minus x2 minus, you just retransform. Okay, and you have to retransform it back to get a solution of the original problem. It's very important to do that. Many students that I've encountered forget to do this, and this shows that you understand one side of the coin but not the other side. So, and you have to do both sides. Right. So that concludes Act 1. Very simple. We just convert the problem, any given problem, from an arbitrary form of linear programming to a standard form. The standard form, to recap, is maximizing an objective subject to ax less than equal to b and x greater than equal to 0. And the important thing is introducing x greater than equal to 0. With this, we are now in a good form, good shape to start LP, to start simplex algorithm and start tackling problems that are in this standard form. Okay, and that's where Act 2 begins, where we will talk about the dictionary, and that's in the next upcoming video.